Hey, how are you? Yeah, good to see you. Yeah, looking forward to talking to you.
Yes. Afternoon. Yeah. All set?
I think so.
Okay, that's good.
Well, good morning.
This is also new blue too, right?
What?
Have you seen this?
I have been here before.
Yeah. Well, it's a great pleasure to introduce Mike Water, and Mike has pretty long history with the lab, and he started here 1992 as a 93, okay, as fellows here, and then he has been moving around quite a bit, and moved to Japan, and for many years, and actually he was responsible for many of our Japan and the Geophysical lab collaborations, especially with Misasas, and we had a great adventures in Misasa and Osaka, Hokkaido's, and that was a great trip with. Yeah, well, it was a great trip. The only thing I remember was the Sapporo beer factory tour. Of course, the earthquake, right? And anyway, and then he moved to Bristol 2004, and he's now the head of the school and for Bristol, and responsible for the big part of the geoscience in the UK, because UK is pretty concentrated on a few of the big schools, and he has been doing great works on the carbon project, and he has traditionally trained as a petrologist, and but he has been moving around, and also in terms of research and from deep mantle to geochemistry, and as well as some of the most recent work and the very impressive diamond inclusion work within a lab on that. And Mike.
Thanks, Faye. I'm going to turn this on. Okay.
Is that on?
Yes.
Is that too loud? Is that good? All right. Thanks. It's always great to be here, and this is a especially interesting week to be in Washington, D.C., so I appreciate it. I'm staying an extra day. This could be a very historic week for all of us. I should apologize. I've changed the title of my talk just slightly. I've changed the word carbon to volatiles, because I'm not going to talk explicitly or only about carbon. It's hard to separate carbon from other volatiles, so I'm going to talk about water as well. Okay? And you get an impression of maybe what I think, where water ends up in the deep mantle from these pictures. A nice diamond filled up with water. This is a synthetic ringwoodite synthesized by people you will know, Dan Frost and Steve Jacobson from BGI. So what I'm going to do is kind of start from, I'm going to try, time permitting, to take a little journey all the way starting from sort of shallow slab environment at a subduction zone. Volatiles make it into the mantle largely through subduction. And we're going to start up in this region and then move down, possibly all the way to the core mantle boundary, time permitting. If not, we might stagnate at the base of the transition zone. We'll see how it goes. This is a slide from Peter Kellerman and Craig Manning's recent paper. In fact, I was at a DCO meeting in Berkeley a year and a half ago. It was like a month after this paper came out, and I'm pretty sure that every single talk had this as their starting slide. It's very useful because it looks at what they did is they tried to quantify, in this case for carbon, what the flux is into the deep mantle. And that's kind of, we won't go through all these boxes, but they put numbers on all of these different inputs and outputs at a subduction zone. And this is the number that I'm really interested in for this talk. And you'll see the number goes from 0.0001 to 52 megatons of carbon. Okay? So fairly large uncertainties there. And I will have to tell you that Peter favors the very low number. And he put this 1 here because I said, Peter, we have diamonds from the subduction, from the transition zone that we know were subducted materials. And I said, okay, 0.0001 then. Actually, there's quite a bit of uncertainty on that number. And a lot of it has to do with diffuse degassing and how you quantify what's coming out of an arc volcano. You can make a similar sort of diagram like this for water, and people that have tried to do that also come up with quite large variations in the amount of water that's subducted. For example, a few years ago, Paul Wallace did some work using melt inclusions, and on the basis of that suggested that there's nearly a mass balance between the water being subducted in a slab and what comes out at arc volcanoes. A recent paper by Parai and Mukpadbehe suggests also relatively small amounts of water make it past the arc front into the deep mantle, such that maybe over the age of the Earth, something like 100 parts per million would have been injected into the mantle. So not a lot, okay? I'm going to provide some evidence that we know that some goes down, okay? And I'll do that in a couple of different ways. So why is it the case that this is such an efficient place at an arc front? I think this diagram explains a lot. It's kind of messy, but we'll go through it relatively quickly. Pressure in kilobars, temperature here. This is for a subduction. This is for the elutions. I could have picked any subduction zone. This comes again from Kellman and Manning's paper. This is based on the thermal structure models of Syracuse et al. 2010. And the important points on this diagram are this. This is a temperature. This is the expected temperature at the base of the oceanic crust, so about 6 kilometers deep in the subducted slab, and this is the top of the crust. This this orangish region over here is water-saturated melting of salt, and this gray line here is deserpentinization. And what you see from this diagram is that there's lots of different subduction zone thermal structures, some of which will, for example, graze the water-saturated solidus, and that's a very efficient mechanism to strip the water from the oceanic crust. And we know that arc tholeiites, for example, have between, on average, about 4% water. So a lot of water comes out of the subduction zones. And the base of the crust then will hit deserpentinization, and models suggest again that serpentine at the base of the crust or in the lithospheric part of the subducting slab generally will break down by around 250 kilometers. Now you can take it a bit farther in phases like phase A, but for the most part we expect that slab thermal structures are such that you're going to hit dehydration, you're going to hit water saturated melting, very efficient removal of water. Now what they were using this diagram for, because it's also contoured here for the solubility of calcite in those fluids. And so you see that at water saturated melting or deserpentinization, this is in ppm, that you can dissolve a lot of carbonate in those fluids as well. So that can also mean that if you've got carbonate in that form, a calcite, and you've got the fluids moving off the slab, that they can dissolve a lot of that, remove it, eventually it will degas as CO2 at an arc front. And this is kind of the basis for their modeling of why we might not expect too much to go down. But I'm going to give you some examples of where we definitely see, well in my view, you can decide whether you think it's definite or not, the evidence for subducted carbon and subducted water. And the first one is diamonds from a place called Dachine. Somehow this has been corrupted. This is in French Guiana. And the location is here. It's just on the northern part of the Amazon craton. This is an unusual diamond location. It is Paleoproterozoic, around 2.1 billion years old. It's deposited in a greenstone belt, and the host rock is very unusual. Actually, everything about these diamonds is very unusual. The host rock looks like this. Okay, this is kind of a messy diagram. Again, here's a bunch of incompatible elements. Primitive mantle normalized. Most diamonds are brought to the surface in kimberlites. Okay? And a kimberlite has a trace element pattern that looks like this. The host rock for these diamonds is highly metamorphosed. Now it's a talc schist. It's an ultramafic rock. It has some textures that are preserved that make it look like it was once pyroclastic. And it has a major element composition that makes it look roughly like a comatiite, which is quite unusual. And its trace elements also are not very enriched, and so here's morb, here's bononite, and here's comatiite. So it's been called a pyroclastic comatiite, which in itself is quite unusual. Okay, so I just want to keep that in mind. We'll come back to this later, this very unusual composition. And it also has, so here's the composition of the host rock, these circles. And here's what you would get if you were going towards ocean island basalts for these particular ratios. This indicates garnet in the source. And this is what you get. This is sort of the trend for island arc type volcanism. Okay, so it looks like the host rock is related to an arc setting. We also know geologically that the greenstone belt has been interpreted as being an arc setting. So what's so funny about these diamonds? This is a typical Dachine diamond. It's very, very complicated internal structures, nothing like you'd see in a normal lithospheric diamond. I'm not an expert at diamond crystallography, but one of our co-authors, Galina Balanova, is. And she says that this typical type of texture, type of texture is typical of relatively rapid growth in a carbon oversaturated fluid medium. Many of the diamonds also show evidence for growth in a high strain environment through their textures, and you can see some of that in here as well. Now, if we look at the composition of the diamonds, this is the isotopic composition here. This is delta 15 nitrogen and delta 13 carbon. Normal lithospheric diamonds, the one that you'd mostly be used to, protatitic ones would fall in this region here, eclogitic runs sort of here. This is the mean mantle for carbon and nitrogen. This is what we find for Dachine diamonds. Okay, and there's actually two populations. One is very light in terms of carbon, but heavy in nitrogen. And also another population, very less abundant, which is around 0 or possibly down to about -5. And this is indicative, at least, of a sedimentary organic carbon. That's what it looks like. The combination of negative carbon-13, positive del-15 falls pretty much in the range of what we'd expect for sedimentary organic carbon. Okay, so keep that in mind. Subduction zone environment, sedimentary organic carbon. Another very unusual thing about these diamonds is in their defect population. So the main defect is nitrogen, and if you don't know anything about nitrogen defects in diamonds, they typically are, they can form in a number of ways. C defects are single nitrogen atoms. A defects, it's a very confusing nomenclature, are pairs of nitrogens. And B defects are tetrads of nitrogen. And over time, a diamond will, when it forms, have single nitrogen defects. And over time, those defects will migrate and form pairs and tetrads. And it's a strong function of both time and temperature. Most diamonds from the lithosphere will have pairs or tetrads. So there'll be A defects or B defects. These diamonds are incredibly unique in that they have a high population of single nitrogen defects, which means they could have never been very hot, or they had a very short residence time when they were formed to when they came to the surface. For example, if we look at time versus temperature, for one of our typical diamonds, which has 40% aggregation to the A aggregated state, what we'd find then is if you were at a mantle temperature, say 1400 degrees or 1300 degrees Celsius, the total residence time of that diamond would be less than a year, which doesn't seem very realistic. At 800 degrees Celsius, however, you'd have 1 billion years. So you can see that there's a very strong function of time in temperature. But this places real important constraints on the history of the diamond, especially for a diamond which apparently was brought to the surface in something that is called a komatiite. Komatiite's a pretty hot magma. So if you were ever at this kind of temperature, you have a few minutes, right? So something's really, really unusual there, and we'll come back to that. They also have very unusual inclusions. We've only found 5 silicate inclusions in the entire population. We're the first ones to find any silicate inclusions in these particular diamonds from Dachine. And these are garnet inclusions, and there's a lot on this, but I'll take you through it very quickly. In terms of their calcium and chromium contents, they are typical of what we would normally associate as an eclogitic diamond. So a lithospheric diamond, which is called eclogitic, has high calcium, very low chromium. It couldn't have been in equilibrium with crititite, but it can be in equilibrium with eclogite minerals. And these diamonds are clearly high calcium, low chromium, and so they're eclogitic. A very unusual thing about them is that they have incredibly high manganese content. So you see them here, spessartine, almandine, grossular. They look something more like a metamorphic diamond that you'd find in an ore environment, with one distinction. They have a very high magnesium content. So they look like a mafic type of garnet. They have a high pyrote content, but they also have this really high manganese content. In terms of their trace elements, these are rare earth elements, lanthanum and terbium. They also fall outside of the range. They sort of at one end of the extreme in terms of these rare earth elements. So pretty much everything about them is unusual. So again, eclogitic, carbon isotopes, nitrogen isotopes indicate subduction environment. Geologically, they look like they're from a subduction environment. Nitrogen defects suggest that they cannot have had a very long residence time or were very cool when they formed. We did a little bit of modeling. I won't dwell on this, but just to show that this is what you'd expect for a garnet in subducted moor. Just a basic garnet clinopyroxene moor. If you sort of deplete that, you get the red line here, and that doesn't match the gray area here is the observed garnet inclusions. The take home from this particular modeling is that you can't really do this kind of a shape unless you've got a trace phase that has a very high partition coefficient for light rare earth elements. And the trace phase that we modeled with was allanite. You could use epidote as well. And allanite or epidote are trace phases in subducted eclogitic material, and they're stable almost to melting of eclogite at the top of the slab. So again, this is very indicative of a subducted oceanic crust. However, what you have to do is you have to explain this very high manganese content. They also have high nickel, and they also have very high cobalt in the garnet inclusions. So everything seems to be saying subducted material, oceanic crust, subducted organic matter perhaps. That kind of puts us at the surface of the slab that's being subducted. So what we've suggested, what we've modeled is that if you're at the slab surface, you've got sediments, that maybe this is subducted sort of VMS type sediments, and that would be the origin of the high manganese, the high nickel, the high cobalt. And we can play with these models and we can get things to work out relatively well with that kind of model using an average VMS deposit type composition. So we end up with these particular diamonds with this kind of a model. This is where the arm waving comes in to some degree. But we know from, and I forgot to mention from the garnet inclusions, that they have a very slight excess in silica, and they are in fact majoritic. And this gives us a way to place some pressure constraint, and the pressure that you get from the majorite content is around 6 to 7 GPa. So this puts them at 200 to 250 kilometers. So that locates us at the slab mantle interface at around 200 to 250 kilometers. So we need a way then to create these diamonds. And the way that we envision is that this is about the depth at which you have deserpentinization in the slab interior. Based on many thermal models, will put you in that range at around 200 to 250 kilometers. So we suggest that fluids being liberated by deserpentinization are remobilizing sedimentary carbon at the slab mantle interface, and then are reprecipitating that as diamond near that interface as well, or perhaps up into the peridotite portion just above the slab. Now, at the same time, because of the nitrogen defects and the limited amount of time that you can spend at any high temperature, we think that the source rock, the host rock that brings them to the surface, must be intricately related to the diamond forming event as well, at least related in space and in time. Maybe not the same fluids, but related spatially and temporally. And so, while we don't have a lot of experimental data to back this up, we do know, at least from a few experimental studies, for example, Kawamoto and Holloway 97, that water saturated melting of peridotite in this depth range occurs at temperatures as low as 1100 degrees Celsius, and you end up with something which is broadly sort of a high pressure kind of bonanite or komatiite. So the suggestion that we have is this is all the action is happening here at the slab mantle interface, and that what we're seeing are diamonds formed at that slab mantle interface, deserpentinization about this depth, formation of the host rock related to that event, and then it all comes to the surface. Okay? So the indication here is that a lot of the water is coming off here, that we do have carbon that can be stable to these depths in the form of diamond. Also, you might have carbonates. I should say we're doing some experiments now to try to look in detail at the reactions that would happen in this kind of model. And yes, we can dissolve a lot of carbonate or carbon into these fluids, although what we've observed is that when they hit an ultramafic mineral, you actually precipitate magnesite and dolomite. So there is a mechanism to produce, to have carbon go deeper into the mantle. And the next part of the talk, we'll look at some evidence for that. So here we are again. We've said that a lot of action happens right here. We've got evidence for carbon being formed as diamonds in this region. Now, in this case, we saw them come to the surface. In other cases, you can imagine that these diamonds would be subducted. Our experimental evidence suggests that you can make magnesite and dolomite, and we'll go deeper, and we're going to look at some diamonds that form now in the transition zone. So these are, we move a bit south. We were up here, now we're down here. We're looking at diamonds from the famous Juina region. This is courtesy of Graham Pearson. Graham and Steve Shirey went to Juina a few, maybe last year or so, and bought a whole pile of these diamonds from local farmers who mine them. And this is what they look like. They're pretty ugly diamonds. They're not used for jewelry or anything like that, maybe industrial uses, and they're willing to sell them for a pretty cheap price. And then you have to thumb through all these and find the ones that have inclusions. And we've studied these diamonds for quite some time now. This is a typical example of the kind of internal structures that you see. Again, they're very unusual, very complicated. They have evidence for growth, dissolution, recrystallization, multiple growth sites. These are all very low nitrogen diamonds. All the super deep diamonds have almost no detectable nitrogen in them. That's a very distinguishing factor. The reason we know they're from the transition zone or deeper is their inclusions. Oh, I misplaced the slide here. We'll come back to that. We'll look at the diamond chemistry very briefly first. In this case, what we're looking at is the del C13 of the diamonds. Again, here's the normal mantle population for diamonds. And we're looking at the oxygen isotopic composition of the inclusions in those diamonds at the same time. And that's what's shown on the y-axis here, del O18 relative to SMO. And again, this is what you get for inclusions in lithospheric diamonds from normal cratonic lithosphere. The inclusions and I'll show you some of these inclusions momentarily, that we've looked at, and the diamonds that they're in, form this kind of array. This is where the slab would be, this is where the mantle would be, and these are mixing lines between those two. And again, we can see clearly indication that the inclusions and the diamonds themselves are subducted. They're recycled subducted material. And the inclusions look something like this. This is a whole variety of them. They are typically retrograde inclusions. They're unmixed from what was once a single phase. And there are a number of ways to put back the bulk compositions. When I started doing this about 10 years ago, I took pictures, made a photocopy, cut them out with scissors, and weighed them. And that actually works pretty well, because now what we've done is we've used synchrotron tomography, and we've looked at the whole inclusion before it's exposed, and can reconstruct it that way, and we get roughly the same answers. One costs about 30 cents, the other costs about, I don't know, $30 million. Anyway, so we find this wide range of compositions. When you put them back together, the two most common ones that we find are majoritic garnet. So here's a garnet and a clinopyroxene that's unmixed from that. You put that together and you get a majorite. And calcium perovskites of various flavors. And they tend to be titanium-rich calcium perovskites. I'm going to concentrate on these two today. Although we've also found things that look like unmixed bridgemanite, and a couple of others which are the CF phase and NAL phase. And these bridgemanites aren't mantle type, but they're luminous Fe3+ rich bridgemanites. And everything here looks like it was subducted, related to subducted oceanic crust. So I won't spend a lot of time on this. This is an old, we've had this idea floating around for some time. In fact, I think I gave a talk on this 4 or 5 years ago, and this would have been the crux of my talk then. We can go through this quite quickly. So this is the calcium perovskite inclusions. This is the abundance relative to bulk silicate earth for a whole range of trace elements again. And what I want you to focus on are these lines here, the red line and the blue line, because that is what a calcium perovskite would have if it was part of a normal mantle assemblage, that's the blue line, or a subducted basaltic assemblage, that's the red line. There's only one location that we found that kind of matches what we'd expect for a mantle calcium perovskite. Nearly all the other calcium perovskites are well overabundant in all these trace elements. So they're incredibly enriched in trace elements, some of them by 3 or 4 orders of magnitude over what you'd expect in a bit of subducted material. And the model that we've, and the same thing is true actually for the majorites. Again, the red and the blue lines are what you'd expect in a subducted peridotite or subducted basalt. And what we find is that majorites from all over the world, not only Juina, are very enriched in trace elements. And so we made a model years ago that suggested that the best way to enrich something in trace elements is a low degree partial melt or a fluid. And these, so what our model was that this is a low degree melt of subducted oceanic crust. It has that flavor of oceanic crust. It needs a carbon component, so we suggested carbonated oceanic crust, a CO2 or carbonate mineral-bearing oceanic crust. You partially melt that. Once it gets to the transition zone, maybe the slab stalls in the transition zone, produces a partial melt, a low degree partial melt. That oxidized partial melt from the slab moves off into the surrounding mantle, which is very reducing. You have a redox reaction, redox freezing, and you crystallize the diamond. At the same time, you have sort of a reactive transport mechanism, which is reacting, so that the carbonate melt is reacting with the peridotite and forming the inclusions that we see. And this all works fairly well. I won't go into a lot of the details, and I'll ask you to take my word for that. Okay. Now the story gets a little bit more interesting. If you look at the majorite garnets, this is all the majorite garnets that you can find from superdeep inclusions. Most of these coming from Juina. This is the majorite component as a function of pressure, and this is how we estimate the pressure of origin. What you see is that most of them, in fact, are really in the deep upper mantle. So some of them come from the transition zone. A lot of them come from between 10 and about 15 GPa. We also have reasons, chemical reasons, to believe the calcium perovskites that we're seeing also, these titanium-rich perovskites, also come from this sort of deep upper mantle to transition zone pressure range. Now our student Andy Thompson a few years ago, what I asked Andy to do as part of his PhD thesis was to melt carbonated oceanic crust and react that with reduced mantle material to see if you can produce the kinds of compositions that we see in the inclusions. Andy, being a very good student, went away and said, you know what, I don't trust any of the melting curves that I've seen in the literature for various reasons, and I want to start with melting carbonated oceanic crust. And so, and one of the reasons he didn't believe it, because most of them had a lot of calcite in them. We need to melt it, we need to put something in so we can see they melt when we make the experiment. And Andy said, no, I want to use an average subducted oceanic crust composition, which has about 2.5% CO2 in it. Made it more difficult to detect melting, but it was more reasonable bulk composition. And this is what Andy found. And so here's the solidus that Andy found. And you see this big depression along the solidus. between around 10 and 15 GPa. And this depression along the solidus occurs because of the subsolidus carbonate phase equilibrium. And that is shown here. You can see these different colors. So down here it's CO2. You don't have carbonate stable in the eclogite. Here's dolomite, magnesite through this region, and then magnesite plus a sodium carbonate phase in this purple region over here. It's the presence of this sodium carbonate, the stabilization of this sodium carbonate, that causes the deep depression along the solidus. And this sodium carbonate forms because as you dissolve clinopyroxene into majorite, clinopyroxene is the major host of sodium in the subsolidus mineralogy. Majorite takes some sodium, but not as much as clinopyroxene. And so what happens is you force stabilization of another sodic phase, and that's the sodium-rich carbonate. Sodium carbonate has a much lower melting point than magnesite, and so it reduces the solidus by hundreds of degrees. Turns out that if you're using too calcium-rich a bulk composition, as many of the previous studies had done because they added calcite to add the carbonate component, that you stabilize aragonite rather than magnesite and sodium carbonate. And aragonite can take copious amounts of sodium, and so you don't see this deep depression along the solidus. Now what I think is very interesting is that if you look again, I've tried to line these up in terms of their pressures, so they should be at the same place. If you look again at where we see the inclusions forming, it pretty much mimics where we have the big depression along the solidus for carbonated eclogite in the transition zone. So we suggest that this is, and what Andy has shown on here are various slab geotherms, so cold, hot slabs down to cold slabs, and they all run smack dab into that depression, except for maybe the coldest slabs. You might be able to get by that. And so Andy will actually call this a transition zone carbonate filter. Very difficult to avoid melting of carbonated oceanic crust in the transition zone. So if Peter's right, and you don't get much down there, we would say that, well, if you do get something down there, and if it's in the form of carbonate, and our inclusion suggests that it probably was, then it's really, really hard to get it beyond the transition zone. So subducting carbonate into the lower mantle may be a real challenge if this is correct. Okay, so I seem to be going relatively quickly, so I will be able to get all the way down to the base. And so Andy comes up with this kind of a general model again, so that we hit that point where we start melting the subducted oceanic crust. The melts move out into the reducing mantle. They form hybrid phases, and I'm not going to show you, unless you have a question I can come back later. I've got a few slides at the end, because he also looked at the phases, the compositions that you would make by reaction, by sort of a reactive transport mechanism of this carbonate moving through the peridotite, and they match our inclusion compositions remarkably well. So again, this is where the diamonds are forming, and they seem as well to become part of the mantle flow, and they move up at some point. I think they probably get deposited here before they're brought to the surface in a kimberlite. And this is why they unmix, and they unmix at relatively shallow pressures. Okay, so I told you I was going to talk about water as well. You probably know this guy. This is Graham Pearson. I think he hangs out here now and again. He was here when I was here 25 years ago. And I'm not sure he's still here, but his ghost is here. Graham works on diamonds and inclusions as well, spends a lot of time working with Steve Shirey. And you probably are familiar with this discovery that Graham made a few years ago. They found the first evidence for hydrous ringwoodite in an inclusion. And this was also from Joina. This isn't it, by the way. But they did find it because as they were looking for inclusions, they noticed this beautiful blue sort of mineral down in the diamond somewhere. And they thought, wow, what is that? And when they did a little bit of a Raman spectroscopy on it, they found out that it was ringwoodite. They did X-ray spectroscopy as well to determine roughly its bulk composition. Did some FTAR, and all the indications are that it's ringwoodite with about a 8.5% water. Okay, so a hydrous ringwoodite in a diamond from the transition zone, first one ever discovered. When they went to polish it a little bit further and try to get at it, they lost it. So it's gone, and it's the only one that's ever been found. But they're busy looking for more. That might suggest that the transition zone has a lot of water in it. I would say no, it doesn't suggest that. It suggests that the diamond-forming medium has water in it, and the reactions that produce the inclusions are forming in a metasomatic region that has water. It doesn't really tell us about the transition zone water content, but it does tell us that water is an important agent in the processes that are happening in the transition zone. So, we've been looking at water as well as carbon. Are there any seismologists in the room? Oh, good. Because this is an egregious sort of hybridization of seismology. It's a perversion of seismology, I'm afraid. This is the beauty of Photoshop, where you can take two different figures from two different studies and meld them together into something that looks like it might have been together. And what you're seeing here is evidence from seismology for a global low velocity region above the 410 kilometer discontinuity. The suggestion is that that is due to low degree hydrous partial melting in that region, causing slow seismic velocities. And the same thing, this is a recent study by Schmant et al., at the top of the lower mantle. Again, low seismic velocities, particular shear wave velocities in this region, and the interpretation has been a small degree hydrous partial melt in that region, which might suggest that the transition zone is actually quite hydrous, so that when you either move material up through the 410, that the water capacity in olivine, basically, in upper mantle rocks, is exceeded so that you produce a low degree melt, and the same thing in the lower mantle, which has a very low water capacity, we think, and so you get partial melting in this region. And so we've been looking at phase equilibrium to try to sort this out. And I'll talk a little bit about that for the rest of the time. So these are experiments that we've done in the diamond ample cell using laser heating techniques and working in a couple of different systems. One is magnesium silica H2O, and another is the same system but adding alumina to that system. And so this one is being projected from water, and the red dots show the bulk compositions that we've used, sort of a model prototype and a model subducted basaltic crust with lots of water in, I should point out. And the main players here are Bridgmanite, phase D, which is a high pressure hydrous silicate, and this new phase called phase H, which is also a high pressure hydrous silicate phase, which has been more recently discovered. I won't take you through all of the detail. I'm happy to answer questions. This is a typical experiment that we would run. This is the temperature. This is microns, and you're looking at the temperature distribution across the laser heated spot in this case. These are relatively cool because we're dealing with hydrous systems. Things happen at lower temperatures. And you see the kind of stability that we have. This is heating from two sides, so the red is one side, the blue is another side, and we can sort of do plus or minus in terms of stability, 20 or 30 degrees Kelvin. And overall, the temperature gradient in our relatively small 25 or 30 micron hole is around 100 degrees. So, and we can hold that for long, long periods of time. We did these and took them to the synchrotron and then looked at what phases we were making. This just gives an example, going from 33 GPa up to 55 GPa. And in this case, we could see we had phase D plus stishovite. As we went to higher pressure, phase D was becoming less abundant, and we were making in this new phase H. And at higher pressure still, phase H eventually goes away, and you end up with perovskite plus stishovite, and you no longer have a hydrous phase. This is in the MSH system. Okay, we end up making what we also are interested in is where these systems melt. All right, and the way we determine determining melting in the diamond ample cell is a challenge. Maybe some of you in the room are working on that kind of thing. I'm glad Riney is not here because I think he would have lots to say. Actually, I wish he was here because I like talking to Riney about melting in the diamond ample cell. What we have used as a primary indication for melting is sort of thermal signal processing. It's been around for some time. And what we notice is that when you melt, and we've got good corroborative evidence of this, and for many systems, you end up with, this is laser power versus temperature, you end up with what's called like a temperature plateau. You get to this point where all of a sudden you're raising the laser power and the temperature's not going up anymore. Anybody in the room do this kind of thing? Liz, okay. Have you observed these?
I do not, but I don't necessarily think this is the evidence.
This is one form of evidence, and not all systems show good plateaus. And also, they show up better when you're working in low variance systems and looking at eutectic or invariant melting points, because you produce lots of melt over a very small temperature range or no temperature range. Okay, and that causes this thermal response. But we don't like to rely on that alone, because there's other reasons that you might imagine that you could have these types of temperature plateaus. And so we also look at textures. For example, here's an experiment which was not at the melting plateau, but somewhere below where we had a plateau, a subsolidus experiment. This is a FEG image for silica, a map of silica and magnesium in this case. And what you see is stishovite, phase D, and MgO in this particular image. And it's a relatively nice uniform subsolidus texture in this case. Then if we take an experiment which exhibited this temperature plateau, what we see is a very different situation. The textures change dramatically. You end up with lots of phase segregation. In this case, it has a lot of stishovite. This is a very silica-rich bulk composition with this annulus of MgO around it, which may be an MgO-rich liquid. We're not quite sure. But we have good textural evidence to go along with our thermal signal processing that, in fact, we are melting these samples. And this is the phase diagram that we produce for the MSH system. These are the two different bulk compositions. They show a very similar result, so we can just concentrate on one. This is the melting curve that we get. This is where phase D is stable. Phase H begins to become stable right here and is out by around 50 or 60 GPa. So it's a very, very narrow stability range in the MSH system. Okay? So the point would be that you could, along some cold slab geotherm, you could have phase D stable up to around 40 to 45 GPa, and then phase H would allow you to take water a little bit deeper into the lower mantle. But when you add alumina to the system, it changes completely. Right? And so this is a lot of data points on there. This is where D is out, right here. Phase H comes in around this same area. We don't have hugely high resolution on that, but it's in around here. And phase H then remains stable all the way to the core mantle boundary. And it does that because it's a solid solution between a magnesium-rich in-member of phase H and an aluminous phase in-member, ALOOH effectively, which is stable to very high pressures. And you have a solid solution between those two, and that solid solution, on the basis, at least of the best we can estimate from unit cell volumes, is quite an aluminous solid solution in these criticitic or basaltic type bulk compositions. And so we expect then in natural critite or natural basalt subducting to the core mantle boundary that you do have a carrier for water all the way to the core mantle boundary as this phase H. Now remember that you have to saturate the nominally anhydrous minerals, perovskite, calcium perovskite, magnesium perovskite, in water before you would produce this. So it's not clear that you'd ever have enough water to do that. I'll make that caveat. This is the melting curve then for a luminous-bearing phase, or a luminous-bearing system, and it's higher where phase H and phase D are stable than in the MSH system, and it's higher because these are aluminous phases, and aluminum stabilizes the subsolidus assemblage. We've also been working on the carbonate system, even though I've told you it's very unlikely that you can get carbonate into the lower mantle. This is really hot off the press. My postdoc gave me this diagram just last week. We've determined the melting curve of carbonate. This is in the system MgO, SiO2, CO2, in the ternary between MgSiO3, MgCO3, and CO2. And this is the melting curve, and this is the subsolidus assemblage. And I'm afraid this turned out to be relatively boring because nothing happens in the subsolidus. We have magnesite, stishovite, and bridgemanite stable through this entire pressure range, all the way to 100 GPa. We really thought we were going to make magnesite too, but we have no evidence for it yet. There is also some other experimental work which suggests that you break down into CO2 in this region. I'm not going to go into it in this particular talk. It's an entire another talk. But what we think is happening in these previous works is that they were actually melting, and that they were looking at quenched products that were coming out of the melt, because all of those experiments in previous works were above our melting curve. So if we kind of put all this together, it looks a bit like this. I've got another student who has been working in the MgO SiO2 system and has determined melting in both the pridotite and the stishovite, or the basaltic side of the eutectics. So here's a eutectic that involves bridgemanite plus periclase plus melt, and this is the melting curve way up here for that system. So that'd be a model pridotite. And now when we look at the hydrous or carbonated systems, we can get a understanding of the solidus depression by adding H2O or CO2 into these systems. And it's massive. It's of the order 800 to 1,000 degrees Kelvin. So here's our MSH melting curve, here's our MASH melting curve, and here's our MSC melting curve. If we put that into context then in terms of what we expect for subducting material in the mantle, here is, I should probably have extended this down, but here's where a cold geotherm would go. So along a cold subduction geotherm, you can keep a hydrous phase in the slab, potentially all the way to the core mantle boundary. But as you heat that material up to a mantle geotherm, which is shown as the gray line here, right? And remember that these are still simple systems, and if we add iron, sodium, other components, the melting temperature is going to come down even farther. The take-home message here is that we would not expect any stable hydrous or CO2-bearing phase, carbonate-bearing phase, in the lower mantle along a mantle geotherm, because it would all be melted. Melt is the stable form of hydrous and carbonated phases in the lower mantle. I think that is all I have. And special thanks to all of these people who are the ones who did the lion's share of the work for everything that I just showed you. And I'm happy to take as many questions as you have. Thanks.
Mike, questions for Mike? So for one of the those cold diamond inclusion, do you see any inclusion which can preserve meteorite? Or do you find any silicate meteorite in the...
Do we have any inclusions that are single-phase meteorite?
Yeah.
We do. We have some from Juina, and they tend to be only have a minor meteorite component. So the ones that we have as single phases give pressures of around 8 GPa. So what I think is that almost everything is eventually transported to 8 GPa before it comes to the surface. The ones that form deeper unmix as they move up. But we also have diamond forming events that are still happening at relatively shallower pressures, and it's probably because you've got hotter geotherms which are intersecting the carbonate solids.
Let's.
Was that seismic feature that your odd figure there, was that seismic axis continuity that you were talking about shallower there?
Which one? This one here?
Yeah. Is that the axis? Is that what you're referring to as the?
This is a global inversion of data looking at velocity anomalies. Just above the 410. In fact, what they do is they put it more around 350 kilometers.
Okay.
If I know from talking to my real seismology friends that if you look regionally and locally, you don't see this everywhere. For example, beneath the Canadian Shield, you don't see any evidence for hydrous melting.
Well,
Or
so
slow
I guess
velocity.
that's what I wanted to ask about because at University of Maryland, for example, Nick Schmer works on this discontinuity, and I just recently heard him give a talk, and he had a whole list of 3 hypotheses about what this discontinuity was due to, and none of them were carbonated melting. They were things like the Defects transition.
Which one are you talking about? This?
At 330, 330.
At 330, 350?
360.
Yeah.
So,
I mean, hydrous melting can work. It's in the right region, although it's a bit shallow. You kind of expect the melt to be right above the 14. And there are places where you see that potentially in seismic data.
For the melting experiment, do you have any control on the water content before you put it in, or after you melt? Do you measure the water content after?
We don't. We have control on the bulk composition that we put in because we add water as brew salt.
Mm-hmm.
So the water content is known in the bulk composition. We've not been able to get any good melt compositions, either in terms of major elements or in terms of water contents.
Other questions?
So if there's no carbon making its way down, what about the super deep diamonds? Would they be primordial?
The super deeps. So my view of the diamond population is that the deepest diamonds that we have good evidence for are just the top of the lower mantle, which makes a lot of sense with respect to the solidus I showed you as well.
Right.
Now there's been some arguments for diamonds coming from D double prime, and that's based on the iron content of ferropericlase in the diamond as inclusions. But ferropericlase is stable from the core mantle boundary to the surface. And you can produce, to me, a more likely explanation for the iron content of the ferropericlase is that it's a result of reactions. It's a reaction. It's not a piece of the mantle.
Right. So there are no diamonds really, no good evidence for diamonds below the top of the lower mantle.
That would be my view.
Then why you're saying the possible bridgegnite and the
No,
those
just-
must be
Just the top of the lower mantle.
top of the lower mantle.
Yeah.
Okay. And
Why are you assuming that the diffusion of elements away is melting rather than some change within the solid state? Or fluorescence?
Well, you mean it could be like Fourier diffusion?
Yeah.
Well, because we can hold an experiment for, say, an hour at one temperature, say 1600, 1700 K, and we get one texture, and it's a relatively uniform texture. We do see physical phase separation in some experiments that we hold for a very long time at much higher temperatures. For example, when we're working in the MS system, we've held some in what we think is a subsolidus for of the order 30 minutes at 3000 Kelvin. And in those cases, we see a clear separation of stishovite and bridgemanite, for example. But then, when we go up to where we see a thermal perturbation, and we quench those, we get a much different texture. And for me, that's fairly convincing, at least circumstantial evidence. We also see it, we do two-dimensional temperature profiling as we go up. And as we're going up in temperature, we can see a very, very uniform and flat temperature field. And it just stays the same, stays the same, stays the same, stays the same. As soon as we get this thermal perturbation, the temperature field completely changes. And while these are all sort of circumstantial bits of evidence, melting is our interpretation. I would also say that when we've done this, used these plateaus and looked at them in situ at synchrotrons for melting of metals, that it also correlates with the onset of diffuse scattering.
Mike, Bob.
Yeah, do you see any evidence for silicon carbide, or do you know of any evidence for silicon carbon, maybe solid solution in some of these higher pressure phases?
There are reports of silicon carbides in diamond inclusions. Any inclusions in diamond, if that's what you're asking. So especially Worth from Frankfurt has looked and done TEM imaging of some complex inclusions that, at a sub-micron scale. And when you look that closely in diamonds, you actually find a lot of unusual phases, very unusual phases, some of which we don't know what they are. And silicon carbide is sometimes present. So we do have very reducing phases sometimes in the diamonds.
Other questions? Oh, Lynn?
Yeah, I was going to ask how much of the conclusions are predicated on the oxygen fugacity conditions in the system, or is it?
In terms of the diamonds?
In
Yeah.
terms of
So-
the phase equilibrium, stability.
Yeah, that's a good question. So in our model, the liquids that you're producing are oxidized. So they're
Right.
coming off an oxidized slab. It's carbonated melting. So we have a carbonated melt that comes off and then into a mantle, which at those depths, because of the solubility of Fe3+ in majorite, should be quite reducing. And so when you have that carbonated melt coming off into that reducing condition, what you're going to do is take some of that oxygen and put it in the majorite as Fe3+, and that's going to reduce the carbonate into carbon. And that works really well. And in fact, in Andy's experiments, where the way he did it was he resynthesized the carbonated melt that he produced in his basalt melting experiments, and he made a layer surrounded by pre-synthesized reducing mantle, model mantle material. So it was synthesized at 14 GPa at reducing conditions. And when he does that, he produces all of the phases that we see, and he actually produced diamond in the reaction as well, along with iron-rich ferropericlates. In fact, I could possibly show you that.
Right, so you're saying melt is the stable phase.
Melt is the
Down,
stable.
you're
Melt is
talking about the
the
oxidized. You don't. Okay.
melt is the
Yeah.
stable phase coming off of the crust. But as soon as it goes into the mantle, then it reduces.
So the whole Rohrbach model
Yeah.
takes over. Okay.
So this just shows what the reaction experiments, and I know this is kind of messy. This is sodium and magnesium number and calcium number, and these are for majoritic garnets. And here's what you'd expect in a peridotite. Here's the majorite you'd expect in eclogites. These are all from experiments. And all the white diamonds here are the diamond inclusion compositions that we see, and they're all between peridotite and basalt. And when you react the melts coming off of the eclogite with that peridotite, you get stuff that's in between. These are a bit, in some sense, you didn't need to do the experiment. You can kind of predict that. And again, we crystallize titanium-rich calcium perovskites. We crystallize majorite garnets that have the same sodium contents, and we crystallize ferropericlates, and we crystallize diamonds in these experiments.
Tyler, you have a question?
Yeah. My question is, can you estimate when the plate tectonics start according to your diamond age?
That's an interesting one, because at least for these diamonds, the Dachine diamonds are, if you agree that everything that we said about those indicates forming at a subduction zone environment and subducting slab, that's 2.2 billion years ago. So that is direct evidence of subduction in plate tectonics at 2.2 billion years ago. Is that the onset of plate tectonics? Probably not. It's probably sooner, and I think Steve Shirey, in looking at his diamonds, has suggested that you have this difference between the age of peridotitic diamonds in the lithosphere and eclogitic diamonds in the lithosphere, and he puts the onset of plate tectonics based on those age gaps at about 3 billion years.
So Liz asked about oxygen fugacity. Let me ask about the role of pH. And around the same time that paper came out, with a pinch of salt and diamond formation, Dmitry Zarinsky proposed forming diamonds as a result of a decrease in pH in some subduction zone settings. And that would help explain in the reaction progress model sort of growth of diamond, resorption, and then growth again. do you see any role for pH? In these?
Well, I do in the sense that I referred to that paper in our Dasheen paper when I was trying to describe what's happening to form those diamonds at the surface of the slab, because it's a tricky problem. Because what we're arguing is that we've got subducted organic carbon, and that has to make it through the initial dehydration front at around 100 kilometers. Okay, and carbon as organic carbon or graphite is quite insoluble in fluids, and so it can make it through, at least at those conditions. But we need to somehow remobilize that carbon and form these new diamonds and form the inclusions within those diamonds deeper down. And so that's where I've brought in some of Dimitri's ideas about dissolving in at high pressures carbon as acetate or lots of different forms that it can form at. And then as that fluid would then move along the slab mantle interface, pH changes as it reacts with the system around it could cause precipitation, resorption, precipitation. It's very complex, and it gets a bit arm-wavy in there. So I have used his ideas as sort of a matter of convenience, if you will, without paying too much attention to the actual chemistry, whether it works.
One other thing would be interesting to look at fruit inclusion, if there is any, and because if this mechanism is true, and you should be expecting hydrocarbon and inclusions.
We have one of the diamonds which looks like it has a fibrous edge to it, and we've been looking very carefully. What we're doing next with these is trying to get some information about these, and we've also mapped them by FTAR, and it's a hydrogen-rich region of the diamond. So that has potential to do exactly what you're talking about.
Any other questions? So Mike is going to be here today and also tomorrow, and if you want to talk to him and individually, and let me know. And also we have a block of time after 4:30 if any of the postdocs want to come to Boyd. Let me know. And otherwise, tomorrow is wide open. You can talk politics or something. Whatever you want. Thank you, Mike, again. Yeah. So how good. How are you? Finally,
what's the situation of the magnetic measurements at the
Could be done. I think TJ is.
The application.